Today I'm going to talk about gas metal arc welding practice on pipe. It's really unusual, and it's been a really difficult thing to find anything on gas metal arc welding on pipe. There's just not a lot written about it. But it's a very common type of procedure. It's a process that I used for 9 years in code fabrication shops, working to the ASME Section 8, ASME B31.3 and ASME B31.1 fabrication codes. What this chapter does, it presents to you a lot of practice jobs that I'm not going to have you do because we have our own practice jobs laid out for you, but I want you to read this chapter and look at the techniques and processes that they use or recommend and see how they differ from what I'm teaching you. Because there's more than one way to walk the dog, as they say. So there will be a number of questions coming out of this chapter. I'll try to keep it short, try to keep it under 45 minutes. I'm not sure how many questions will be on the test, probably between 20 and 30. But as we go through here, I'll have a lot of things for you to highlight. And when I think we've come to a really important item, I'll ask you to bullet that. And then when we're all done, if you have any questions, just get with me and I'll see what I can do in terms of answering those. So let's start on page 899. And I'd like you to go down to almost to the last, about halfway through that last paragraph. And it says, the practice jobs in this chapter specify techniques for carbon and steel pipe. Pipe is available in such ferrous metals as low and high strength carbon steels, wrought iron, carbon molybdenum steels, chromium molybdenum steels, low temperature steels, stainless steels, and clad and lined steels. Pipe is also available in such non-ferrous metals as aluminum, nickel, copper, titanium, and their alloys. Now I want you to highlight these next two paragraphs. Bullet. Welding may be done in all positions using the gas metal arc welding process. The direction of welding for vertical welds may be up or down. The usual practice is to weld the first pass down, followed by passes that may be welded up or down. Depending on what you do, you still have to have a qualified procedure. If you're going to put the root pass down and then go vertical up, well, your procedure has to specify that. And if not, you have to qualify a second procedure. So they're not interchangeable. You have to have a procedure for each one. It has to be written down, it has to be documented. The mechanical tests have to be done on it. So don't think that you can freely change from up to down, because you can't. It's against the code. It would be a code violation. It is not difficult to obtain radiographic quality welds. The MIG and MAG pipe welding process is used extensively on both non-critical and critical piping, in which the weld must meet requirements of the codes for such critical applications as nuclear piping, steam power plant piping, and chemical process piping. Go over to the next paragraph where it says advantages. The process is fast and in many instances faster than other welding processes. The elimination of slag and flux reduces the cleaning time considerably. Heavier passes can be made, thus cutting down on the number of passes per joint, and of course that depends in large part whether you're going vertical up or vertical down. Since the electrode is continuous, fewer starts and stops are necessary. It's not uncommon at all, it wasn't uncommon at all for me to start a pipe weld with a welding partner. We'd each get on one side and one of us would fire up, and then a second later the other one would fire up, and these would fuse on top, and then we would come down and we would have to time it so that one of us could move a little faster and get done across the bottom before that second guy got down, and we would go all the way from the top like so, and we would turn that gun and walk it back down underneath like so without stopping. So it is a pretty neat process, but it takes practice and a good back, because you got to get into some pretty awkward positions when you're welding in a fixed position. The process can be used on all pipe sizes and pipe wall thicknesses. Weld metal is high quality and meets requirements of most codes. It is considered a low hydrogen process. Weld appearance is good penetration, fusion, and a smooth weld bead can be produced inside the pipe on the underside of the root pass. We used to say it looks like a roll of nickels, and we lay it in there so nice. Backup rings may not be required. Because of the concentration of heat when welding, distortion and warpage are reduced. Bulleted item, the root pass is thicker and stronger than that produced by the TIG and stick electrode process, so that the danger of the first pass cracking is reduced. And that's particularly true on the uphill. When you're welding downhill, that root pass is not very thick, because downhill you're not going to carry as much metal, but downhill is faster, downhill is smoother, puts a really nice bead in there. So there are some things that these authors have said in here that I don't particularly agree with, but just let me point that out to you. If you are going vertical up, you will get a thicker root bead. Vertical down, I'm not so sure. Use of equipment and supplies. Highlight this part. It says the equipment needed for the gas metal arc welding of pipe does not differ in any way from that required for other forms of MIG or MAG welding. Then it gives us what those items are, those bulleted items. That's the equipment you need. Then highlight the remainder of this column, the next column. It says the engine-driven generator is suitable for outdoor welding applications such as pipelines and bridge and building construction, and in locations where easy access to electric power is not available. These welding generators are capable of generating 120 or 240 volts auxiliary power for running power tools and lighting. The inverter power sources are portable and have enhanced arc performance to allow for all modes of transfer, including short-circuiting, spray, and pulse spray. In many cases, they have inductor controls, and with microprocessor technology, have the ability to shape their output waveforms. They can have stored programs, which ensures that many of the essential variables are being followed per the welding procedure. These can be actually programmed into those machines before they ever leave the factory. The DC rectifier is found in fabricating shops where the input power supply fluctuates very little. It is quieter than the other output sources, and it draws current only during welding. That's a bulleted item. It is an advantage to use a machine with variable slope control and variable inductance control. It should also be equipped with a hot start feature, which enables the welder to select a higher voltage for a timed period at the beginning of a pass or at a new start. A hot start ensures good bead contour and the elimination of discontinuities caused by a cold start, which would be lack of fusion. So that's another bullet in there. Next page, bottom of the column, highlight that. It says the welding gun may be equipped with special nozzles and contact tubes. Because of the groove welds typically done in piping systems, access to the root of the joint is critical. Special tapered contact tubes and nozzles greatly reduce aid in getting complete fusion. In many cases, the contact tube will be flush or slightly protruding beyond the end of the gas nozzle. This ensures that the proper electrode extension can be maintained while allowing a welder a good view of the weld pool. And it's kind of tough, actually. I've had a difficult time in finding the kind of stuff they're talking about. What you have here, and then in a cutaway, and then here's your cup. This is what we would normally use for a gas metal arc. It'd be tapered something like that. Here, this is your wire. Here's your contact tube inside your cup, and you can see this is kind of bulky, and you can't get down into a joint like this very well with something like that. So what they're talking about is they have nozzles that will come out and they're tapered down like so, and then you can put that contact tube right out there on the end, so that this finer taper allows you to get down in here and make that root pass. And these cups, as you probably know by now, sometimes they'll come with an insulator attached, or the insulator could be separate. The ones that have the insulator attached are preferable when you're welding pipe, because pipe is really critical. But if it's got the insulator attached to the cup, then you're not going to get any wobble. It's not going to be loose and sloppy. If you use something like this without an insulator attached, this contact tube can easily swing over here and touch the sides of that, causing a short circuit. So that's a little heads up for you, and that should all be highlighted in your text. Then on page 903, highlight everything under shielding gas. There are 3 bullets under shielding gas, so read that thoroughly and understand that. Gas flow rates, highlight this portion. Says, be sure that you have the correct regulator and flow meter. The calibrations of such equipment are designed for specific gases. The gas flow rate is the key to good gas shielding. A rate of 15 to 25 cubic feet per hour is adequate for most indoor welding operations. However, if you drop down, it says, if you're outside or you have any kind of a disturbance, you want to increase your gas flow rates by 5 to 10 cubic feet per hour. And then it says over in the top of the next column, which is a bullet, in some codes, wind speeds over 5 miles per hour require draft shields, or what we would call a hooch. You would build a little house around yourself out of bisqueen and 2x4s. Filler wire, bullet. Pipe is usually welded with E70S-3 or E80S-B2 filler wire. If you remember from our discussion of electrode wires, that B2, that suffix, is telling you that that's got probably, I would say this one has some chromium in it. But it could be, depending on that suffix, you could look it up in your book and see. It could be chromium, it could be molybdenum, it could be a little bit of nickel, but I think it's chrome. A wire diameter of 0.035 inch gives the best results. It enables the welder to control the weld pull better than other sizes do and gives him or her more leeway in torch manipulation. And I'll vouch for that. Most of the gas metal arc process piping that I have done, we did with 035 wire, and it's a really simple wire to use, good quality welds. However, some shops think that there's a better trade-off going with 045. They're trading off higher welding speeds, higher deposition rates, against the possibility that you could get discontinuities, lack of fusion primarily, and porosity. So some companies will use an 045 wire. What we're using in our shop is 035. Edge preparation, the surface of the pipe end must be smooth and the edge must be square with the pipe length. A poorly prepared pipe end can be the cause of an unsatisfactory weld. A bevel of 37.5 degrees is widely used in industry for the ASME boiler code welding. The American Petroleum Institute recommends a 30-degree bevel, but a 37.5 degree bevel is sometimes used. Let's see, flip the page to 904. You know, before I go any farther, I want to draw your attention to that picture on page 901. And if you would, take a look at that picture. It's the same one I've got on the board here. This is a typical setup. Now this welder, it's hard to see in this thing that I made, but he's got a positioner here. And a positioner is, it's a metal table that can rotate up and down, and he's got it rotated in a position where he can keep this pipe level. You can't see the end of it, but out here on this end, he would have a set of rolls to support the far end. And he's got pipes. He's got a flange right here, and then he's making a pipe weld here, and then there's another pipe weld here, and then another pipe weld here, and then a reducer, and then another piece of pipe. Well, you got to fit all of that up, and you're going to fit it up, and then you're going to use a crane, and you can see he's got a metal crane right here. This is one of those hand ones where you got to sit there and you pull the chain. It's a chain fall actually. Kind of wears you out a little bit, but some shops that's about all they're going to have. So he's used this chain to raise this thing up, hook it up to his pinwheel, put his rolls underneath, and now he's got his little Hobart welder here with 035 wire, and he can weld everything in the flat position simply by using his speed control, and you can see that hanging right down here. This is his motor speed control that he can use to adjust how fast this thing is rotating. I usually used a foot feed. You could step on a foot pedal and increase or slow down how fast that stuff was rolling. But before you get to this point, you've got to fit all that up. And that's the tough part, is getting it all fit up square. When you're a welder, you're not just a welder. You're a fitter as well. And you've got to be able to line that stuff up. Now, if you've got something like that, and you've got to line it all up, well, how are you going to do it? You got your flange here, and then a piece of pipe, and then maybe a reducer, and another piece of pipe, and so on. And then finally you get out here and you've got your set of rolls. Well, you've got to get all this in line. Well, one way to do it is to put a tab here and a tab here, and you can actually draw a string between those two, and you measure the distances to make sure that the distances are the same. And you can tell from this if it's lined up properly. And you would also do the same thing on the side so that it looks like this on the side. And you can measure the distance from here down to the pipe, and then from here down to the pipe. So if you have two pieces of pipe, you can actually make sure that they're aligned in those two dimensions, and then it'll be square. And then, of course, you've got to tack all of this stuff up. You tack it all together and make sure it's and lined up, and you got to put good strong tacks in it so that it doesn't warp or distort as you're welding. And then when you're welding, you may make a weld right here, then you're going to roll it over. You're going to roll it some more and put this end up, and you'll make that weld. So you're balancing the shrinkage forces and the heat forces, and then you might come back here and do that one and then that one and get your root pass in. And you might do that on all of those before you go back to fill and cap it. So there's a sequence that you've got to follow, because when this thing's done, it'll probably load up on a pallet and be shipped to some job site and installed. And if it doesn't fit up properly, who's the one that's going to get the blame for that? Of course, your quality assurance person should check that out. And also on these flanges of course have bolt holes in them, like so. And these bolt holes usually have to be what they call two-holed. That is, these top two holes, and you can go right down there. You can draw a straight line between those holes. If you had like a coupling right here that went down inside this piece of pipe, the top of this coupling may have to be square with the two-hole on that flange, because they might want, when it gets out to the site, they might want to put a valve or a spyglass or something on it. So you have to make sure that everything is properly aligned in that term as well. And then finally, you've got to make sure that the face of this flange is square with this. Is it at 90 degrees to that pipe? So there's a lot more to doing this than just making welds. Nobody just welds anymore. You've got to be able to do pipe layout and fit up. So if you haven't taken Weld 2540, take it, because we talk some about how to do this sort of thing. And I've also got a video lecture where I demonstrate some of this stuff, even if it's unrelated to what you're doing. Even if it doesn't fit into one of your classes, ask me about it, and I'd be happy to get it for you, and you can see some of the techniques that I demonstrate in that for doing this sort of thing. So just something I wanted to point out to you. Now let's go ahead and go back to where we were, which is fit up and tacking. Let's see, is that where we were? There. Let's see, wire operated shielding gas. Okay, so we're on page 904 now. And it says, read that part there that talks about beveling, and I want you to underline this. It says, I'm on the third paragraph. It says, if the root face is greater than 1/16 of an inch, adequate penetration cannot be obtained using the MIG process. So you don't want hardly any land on there at all. It says, some welders like to use a V shape and increase the root opening. You will recall from your past practice that the root bead is the most important bead, and that proper edge preparation is necessary to ensure good root penetration. So read that entire paragraph. There's one bullet coming out of there. Now we're on fit up and tacking, which is kind of what I was just talking about. Highlight this. There's a bullet. It says, in setting up the weld joint for work according to the ASME code, make sure that the root opening is no less than 3/32 of an inch and no more than 1/8 of an inch to ensure adequate penetration, and no land. And especially if you're doing vertical down, this is what you want. Now, if you're going to go vertical up, that's a different subject. As I said, you have to have different procedures if you're going to go vertical up or vertical down. If you're going to go vertical up, you can have about a 1/16 land, and you can have it a little bit tighter because the amount of heat input is concentrated a little more when you're going vertical up. But for vertical down, these dimensions are what you want. It says, on pipeline work, according to the API code, it is common to use higher currents than in the shop. A good root opening of 1/16 to 3/32 of an inch is used in order to limit excessive melt-through on the inside of the pipe. Tack weld should be a minimum of 3/4 of an inch long and preferably about 1 inch long. Again, so once you get that stuff fit up and in position, you don't want those tack welds breaking when you start to move it around or put it on a chain fall or start welding on it. Highlight this entire next paragraph. It says, both ends for all tacks should be feathered by grinding as shown in figure 24.9. There are two important reasons for feathering. One, to remove any possible defects in the ends of the tack, and two, to reduce the mass of metal at the ends of the tack and therefore ensure good fusion of the root bead to the tack. 4 tacks are all that are necessary for diameters up to 12 inches in diameter. So 1, 2, 3, 4 bullets out of that section under fit up and tacking. Interpass cleaning. I have 3 bullets coming out of here, but I'm going to pick it up right here in the middle of the first paragraph where it says, Although there will not be a heavy flux deposit to remove, there will be a little dust and a black glossy material in spots on the surface of the bead. The material should be removed with a power wire brush. If the materials are not removed, they will become entrapped in the weld, causing porosity, and the arc will be unstable. And what that little glossy stuff is, it's silicone that's coming out of the weld metal. And you're going to have to follow that off. Not only can you trap it in there, but if you try to weld over it, it won't break down, but it'll make your welding wire sputter because it can't burn through it to make contact with the base metal. So make sure you use a wire brush, a power grinder brush, and get that off there. With either vertical up or vertical down progression techniques, the root pass will generally require a good deal of grinding. When the root pass is being made, little attention is paid to its weld face contour. What is being focused on, and this is a god-awful truth, what is being focused on is good root penetration is occurring on the inside of the pipe. The root pass must also have good fusion into the groove face as well. And I've got a really sweet video, it's a nice overlay. I'm glad they put this one in here because it really shows it good. I'm going to jump ahead a little bit for this one. Now this is what they're talking about. This is actually on a head, and this is on page, let me see. This is on page 914, upper right-hand corner in your textbook. And this is the inside of a large diameter pressure vessel, but it's not very thick. And what they've done, what this picture shows, is a root bead done with MIG and how it's fused into the sides. And in your picture, you can just barely see some of that glossy black stuff on here, which is silicone. And you're going to get that on both the inside and the outside of that. But on the outside is going to really be humped up like this as you put that root bead in, and then you're going to have to grind that down to clean white metal in order for you to deposit your next pass. But we don't care about that. This is what we care about. This is the important thing, that it's breaking everything down. You can see these straight line edges here on the part that hasn't been welded yet. You cannot have any straight line edges here. Once that weld is put in there under ASME, you cannot have any straight lines. You've got to break it all down. And what you're going to see in here is you could get little fish eyes that I've talked about in previous lectures. You could also get what we call whiskers, where some wires are sticking through. Those are not allowed. And you could also get lack of fusion along the edges. So that picture that's in your textbook is a quality weld. And what they're going to do with a large head like that is they're going to put maybe 1 foot of weld in there after they got it fit and tacked. And then they're going to rotate it some, and then they're going to put another 1 foot piece in there and rotate it some more, put another 1 foot piece. Again, they're going to balance those shrinkage forces and tack it up in different places, weld it up in different places, instead of starting in one place and just rotating the entire thing around to put that root bead in there. They'll rotate it all the way around once that first root bead is in there, because remember, your root bead is your most critical and important bead. And before you zip it up, you're going to take a look through this root opening with your flashlight, and you're going to inspect all the way around the circumference of the inside of that head and make sure it passes your visual inspection. You are your own best inspector, and you've got to check that and make sure it's right. Okay. So, 3 bullets coming out of there on inner pass cleaning. Then flip the page to 906 and take a look at table 24-3. Which is this. And I wanted to throw that up there to draw your attention to a couple of things. The most common things, it says troubleshooting for gas metal arc. What are you going to encounter? Mostly you're going to find number 3 and number 4. Those are the ones that as a craftsperson you're going to encounter in your welding. So what causes it? Scattered porosity. Scattered porosity, it's failure to remove large islands of silicone glass that we've talked about. How would you remedy that? Use a power wire brush to remove the glass and clean prior to welding. And then this is probably the most common one, oil or other foreign material on the pipe or the electrode. And also you got to remember that those electrodes, those spools of wires, they sit on those machines for a long time. and they collect dust and other particles, and that can be dragged into your liner and then eventually deposited into the weld, and that can cause porosity. Gross porosity would result in cluster porosity. That would be due primarily to a loss of your shielding gas. This troubleshooting guide says breeze blowing shielding gas away. So that would be another one that cluster porosity would be caused by losing your shielding gas. Scattered porosity is oil and foreign materials. Wagon tracks is failure to remove glass from the edges of the previous pass, and then a convex root or fill pass. So if you have a convex, if you remember what convex means, let me draw a picture here real quick. Let's say that this is your joint, and you got your root pass in there, and when you put your root pass in, remember, it's liable to come out like this, because you're focusing on this inside edge to make sure it's right, and you're not really too worried about this. Well, if you don't properly remove that before you put the next one in, you won't reach down into the bottom of these little V's that are formed. And if you don't reach down into those bottoms, then you can get wagon tracks in there. Lack of fusion, a void would actually appear on your film from that. So you want to make sure that you take that down nice and smooth and blend that to nice clean steel, white metal, before you put your next pass in there. Okay. So, still on page 906, read about horizontal pipe axis roll position welding. This goes actually, it goes all the way to page 909. And I have got 1, 2, 3 bullets in the first column on page 907. In the second column, highlight the second paragraph where it reads, each time the weld is restarted, it is necessary to tie in with the previously deposited bead, and you have to do that carefully. Read about that. Read about how to make your tie-ins. And of course, I'll talk with you and show you in the lab how it should properly be done, but read about how they want to do it. And then it says, a stop in welding a root pass in an open joint can cause shrinkage, cracks, cavities, and cratering. So that's a bullet. Flip the page. Bottom of 908, it says, grind the weld face to make sure that it is flat. Grind the toes to eliminate any undercut or incomplete fusion. The surface of the weld should be flat, and brush the weld before applying the next pass. So we've got one bullet off of that. Now, under filler pass, it says, start the second pass about 2 inches past the original starting point for the root pass. Okay, this goes on to talk about staggering your starts and stops. And what happens, very briefly, if you've got your weld, and let's say this is film, okay? This is X-ray film. Okay, and they're going to X-ray the weld that you just put in there. Well, if you have a whole bunch of starts and stops in one little area, you might have some porosity, you might have some lack of fusion, you might have some silicone inclusions, and the way they read this film is they read it by the square inch. Okay? And the ASME code allows so many discontinuities per square inch. Well, if you have all your starts and stops in the same place, you've concentrated those discontinuities right there. And by concentrating them, you may be outside of what's allowed. But if you stretch those starts and stops out, and you had one here, and then another one over here, and then another one over here, well, now it might be acceptable. Okay? So you don't want to concentrate your starts and stops, you want to stagger your starts and stops. There is a bullet coming out of that paragraph, so read it carefully. Cover pass, make the cover pass like the filler pass. Be sure to pause briefly at each edge of the filler pass to obtain proper fusion. The bevel edges on each side should be your guide to determine the final width of the cover pass. Remember, we just barely want to go over onto the surface of the parent metal. Last paragraph on this topic, it says, after preparing the test coupons, bend them on the standard test jig. The weld should show no separation of any kind. That's what will get you more than anything else. Always remember that gas metal arc welding short circuit, what we're doing, it has the lowest amount of heat input of any of the welding processes, and therefore it is greatly susceptible to lack of fusion. That's why when you take a test, most companies will first x-ray your work they'll look for porosity and stuff like that. But then they're going to take it and they're going to bend it. because an X-ray usually will not show lack of fusion. You've got to have your source oriented just exactly right to see that lack of fusion. So they'll bend it to see if you have any of that. Okay, under vertical pipe axis fixed position, go down to where it says root pass, the middle of the paragraph, highlight it and a bullet. It says carry your wire on the leading edge of the pool to get complete penetration. Make sure that fusion is taking place along the root edges of each pipe bevel. Also make sure that the weld does not sag along the bottom bevel so that it causes overlap in incomplete fusion on the bottom edge. Also be careful not to undercut the top bevel. Penetration through the back side is necessary. What they are talking about there, if I can find my rag. Remember, we're talking about the vertical fixed position. So it's a 2G, but the pipe is like this, vertical fixed, but you're welding around like this. So your joint's going to look like this, and you've got to get complete penetration. Well, what they're worried about is when you're putting that root pass in, they're worried about some metal running down on the inside of the pipe like that, not fusing. That's overlap. Your book's calling it sag. That's a non-proper term. It's actually called overlap or lack of fusion right here, which is not allowed, of any kind, is not allowed under the ASME code. And then the other thing they're afraid of is that you're going to get undercut here on the upper edge. So I'll show you the proper technique, proper way to do that. If you've already taken basic gas metal arc welding on plate, I've probably already discussed this with you. Anyway, there's a bullet out of that part. Flip the page, filler passes, highlight all of that under filler passes. Filler passes and cover passes on page 910. Under horizontal pipe axis downhill, this is a bullet, let's highlight this. It says, in this position, commonly referred to as the bell hole position, the 5G position is referred to as the bell hole position. The pipe axis is horizontal, and it's not turned as the welding progresses. The bell hole position is encountered in all types of pipe installation. Travel may be uphill or downhill. The downhill welding technique is employed in cross-country transmission blind piping, and the uphill welding technique is employed in pressure and power piping and in general construction. Either technique produces sound welds, but the downhill technique is faster. When welding downhill, some welders find it difficult to keep the weld metal from running ahead of the weld pool. And proper practice and proper technique, which I will show you, will stop that. I've got three bullets out of that part that I have just read. Now let's drop down to the middle of that column where it says, make sure that the pipe has a root opening of 3/32 of an inch all around. This root opening is most important and must be maintained. Feather the tack welds so that they do not become an obstruction when you pass over them with the root pass. So highlight that. There's a bullet out of there. And then on the root pass, highlight all of that, the remainder of that page. And I've made a note here to myself. It says, grind starts and stops and feather for good tie-ins. So there'll be two bullets coming out of there. Flip the page to 912, bullet, highlight. The downhill technique of welding is preferred for the root pass, but if the fit-up is close, the uphill technique is employed. But again, as I've already previously mentioned, you cannot employ that at random. You've got to be working under a qualified procedure, okay? Unless it's non-code work. Filler passes. Here I've made a note to myself, the current may have to be increased slightly on your filler passes, and this is true. We did it a little more than slightly. We cranked it up pretty good on those filler passes. You can turn it up too much. So you want to be careful not to turn it up too much, because if you turn it up too much, you're going to be dumping a lot of metal in there and you'll actually get overlap instead of lack of fusion. Instead of good fusion. So again, I'll work with you one-on-one to make sure that you understand what we're looking for. Highlight the top of this paragraph. This first paragraph says, start welding at the top outside of the area of the previous starting point. Again, we're staggering. Stop at the bottom outside the area of the previous stopping point. The second pass is made with a straight weave by moving the gun from side to side and pausing briefly at each edge to each edge of the underneath pass. Do not depend on the metal to wash up on the sides of the groove. In order to avoid overlap and to secure complete fusion, the electrode wire, the arc, must be directed toward the surface to be joined. Then clean and inspect it. So you can't just hope that it's going to wash in there and fuse. You've actually got to point it. Always keep in mind, lack of fusion, lowest heat input. It's the primary drawback of gas metal arc. Drop down to where it says cover pass, last sentence in that first paragraph. It says the bead should have about a 1/16 convexity, and it should taper out to the edges of the bead. This is all highlighted now. It is important to keep the arc ahead of the pull when doing the filler and the cover passes downhill. Any attempt to slow down the travel speed in order to deposit more weld metal allows the molten pull to run ahead of the arc and causes overlapping or incomplete fusion. Keep the metal thin. The maximum pass width that can be handled with any degree of success is 1/2 inch. Split layer passes are necessary beyond this width, meaning you'll put a multiple weave in. And I've got two bullets coming out of that portion. Vertical uphill travel here, I've simply highlighted starting in the middle of the second paragraph where it says start at the bottom at 5 o'clock or 7 o'clock and weld across the 6 o'clock position and then up toward the 11 o'clock or 1 o'clock position. So you're going to start on the bottom and weld up. And again, we're not starting on the bottom dead center. We're staggering. And let's see. Depending on the side of the pipe from which you're welding. It says, then I skipped a couple of sentences and picked it up, highlighted where it says, weld passes should not be more than 1/8 of an inch thick. And we're talking about vertical up now. 1/8 of an inch thick. The filler passes should have a flat face, and the cover pass should have a slight convexity reinforcement of about a 1/16 of an inch. Remember, you're allowed up to 1/8 of an inch. But the smaller it is, the less of a stress riser you're going to have. I want to show you another overlay, and this is our last overlay, because I just think this is a great picture. Brings back a lot of memories, because I built a lot of this stuff that you're looking at here. Now, this is a heavy wall pressure vessel built to Section 8 of the ASME code, and you can see this is the compound bevel that I talked about before in previous lectures, and you can see how thick that head is. Well, you have to weld a dog on this thing and pick it up with a chain to get it into position, and it usually takes one person to assist you to get that first tack in, and then you'll put another dog with nuts on it, with bolts on it that you'll use a crescent wrench to swing this thing back and forth like a pendulum until you line it up, and you'll use a straight edge then to measure all the way around this to make sure that the head is lined up with the pressure vessel itself, with the body of the vessel, and then you're going to tack it in various places. Then you're going to use a high-low gauge to go into this root opening to check your alignment. Under the ASME code, you're allowed a 1/16 of an inch of misalignment. Now, on this thick stuff like that, a mismatch is really not too much of a problem because they counter-machine these, counter-bore them to match the ID, and it works pretty good. Where you come into the problem is if you're welding on like a 1/4 inch pressure vessel or a 3/8 inch thick pressure vessel. Those things have a tendency to warp, and you may not, as you're fitting them, they'll get out of round, and that makes it kind of tough, and sometimes you can get some pretty bad mismatch on that thinner stuff. This thicker stuff, however, it's pretty nice to weld. And again, as I mentioned earlier, they put a part of the root in and a part of the root in, and that's the way they're going to do it all the way around until they get it secured, and then they'll finally zip it up and clean it all up, and then it's ready to put a hot pass in. And something this thick then would probably go over to the next operation, which would be submerged arc welding, and they would fill this up using the submerged arc welding process. Okay, I just wanted to point that out to you because it's a great picture. Almost done. We're on our last page. Under intersection joints, jobs 24-J9 through J14, I just wanted to mention these to you because they're talking about T, Y, and K joints and laterals, and they're found in pressure and powerhouse installations. Read about how that is, because the AWS D1.1 structural welding code addresses T's, Y's, and K's, and they have different procedures that they want to use for that.
And then finally over here in the next column, highlight the last paragraph. There's a bullet coming out of here. It says, you are again instructed to take extreme care in making the root pass. Be sure that there is penetration to the root of the joint and the fusion to the pipe surfaces. All other passes must be fused to the underneath pass and to the pipe wall. When multiple pass welds are necessary, make sure that all starts and stops are in different areas. The starts and stops must not be at the same point. So over and over and over again in this, they have stressed that you have to point the electrode where you want that fusion to occur. They've pointed out that the root pass is the most critical, and they have stressed that you have to stagger your starts and stops. So those are all things that you should remember for this upcoming test. If you have any questions, just get with me. If this chapter has brought any questions to mind, bring them up whenever we're working together in the welding booth, and we'll talk about them. Thank you very much for your attention.